So let's look at the acid catalyzed hydration of alkynes. Now, to review and to show the analogy between this and the previous unit, um, if we take an alkene and add water in the presence of acid, we do a Markovnikov's addition of water across that double bond. If we try to do this with a terminal alkyne, this is usually a very slow reaction. So we need something else. In that case, that something else is going to be a catalyst that we're going to throw in to help speed it up. So you'll see that the reaction conditions are somewhat similar. We'll use acid in water, but then our catalyst is going to be mercury sulfate. And if I use the pattern that I've seen in this whole unit and comparing it to reactions with alkenes, you might think, well, this should be our product. OH goes to one side, hydrogen goes the other. It does a Markovnikov's addition. And you wouldn't be completely correct in this. Because what happens is this product, which we call an enol is an alcohol on an alkene, is not very stable and will often isomerize to make a ketone or to make a carbonyl. We call this process tautomerization. It's kind of a mouthful. But that carbon-oxygen double bond is most of the time more stable than a carbon-carbon double bond. And so what we have is this equilibrium between the enol form and the keto form. Hence why this is called keto-enol tautomerization. And this is the product that you would show, both on homework or quizzes or exams. That's what the intended product that you would need to show. Let's talk about how this happens. We're going to start with our enol form. And since there's plenty of acid floating around, we're going to do what we did all throughout chapter, or our last unit, I should say. And we're going to use those pi electrons to pick up a hydrogen. And now we're going to use resonance to make a pi bond. And then finally, just do a proton transfer to get to the keto form. Now, I want to highlight something important here. These are not resonance structures. I want you to think about why that is the case. Why are these not resonance structures? Hopefully the answer that's coming up in your head is, well, you moved atoms around. Remember, we don't move atoms in resonance. If we move atoms, then it's no longer resonance. And so these, what we call tautomers, the enol and keto tautomers, are constantly interconverting through to each other. It's just that this conversion is very favored towards the keto side. The equilibrium favors the keto side instead of the enol side. Now we see the same thing if we have a internal alkyne. We just can't follow Markovnikov's rule. So we'll do an acid catalyzed hydration. And what that means is that the carbonyl could end up on this carbon or it could end up on that carbon. Now for this particular alkyne, because it's symmetrical, it ends up being the same. Okay, so these are the same product. But if it were asymmetrical, then we would end up with a mixture of products because the carbonyl could go here on the third carbon, or it could go here on the second carbon. So there it is on the third carbon, or it could go here. And we don't really know what that product mixture is. It's don't assume it's going to be 50-50 because it's not. It's not like we're not dealing with stereochemistry here. Some of it will go to the third carbon, some will go to the second. We won't know what that product mixture is until we actually go into a lab and do that. So we have to be very careful and knowledgeable about if it's not a symmetrical alkyne, symmetrical internal alkyne, then we will get a mixture of products. Now, this whole, or most of the beginning of this was about doing a Markovnikov's addition of water across an alkyne. You might remember that we could do an anti-Markovnikov's addition of water to an alkene. Again, let's look at a review here. If we take an alkene and do a hydroboration, oxidation, we could do an anti-Markovnikov's addition of water. Can we do the same thing for a terminal alkyne? And the answer is yes. We just have to be, we can't, it's a very similar reaction. We can't use borane though. We're going to use a kind of modified boron reagent called Ca2BH. You don't need to worry about the structure or anything like that. It's designed because we have more pi bonds in an alkyne, we don't want the boron adding multiple times. We only want it adding once. And so this borane reagent will only add the borane and the hydrogen once. And then the second step is still on oxidation, which, by the way, for step one, that's not named after the singer. That's the acronym for the carbon chains that are attached to the boron. I recommend looking it up just to kind of get an idea of what the structure looks like. But just like here in the hydration of an alkyne, we ended up with an enol. Initially, that is the product that's received here, where we do that anti-Markovnikov's addition. But that enol form is not as stable as the aldehyde form. And the way that this tautomerization works, since we're doing this in basic conditions, we're going to deprotonate here. And then these electrons will come down to form a pi bond. These pi electrons will pick up a hydrogen from water. And that gets to our keto form, or in this case, an aldehyde. So again, this is the product that you show. You always show that carbonyl form. So to kind of summarize the whole page, depending on if we start with a terminal alkyne, we can do a Markovnikov's addition of water. And end up with a ketone. Or we can do an anti-Markovnikov's addition using a hydroboration oxidation. Just keeping in mind that we end up with an aldehyde because it's an anti-Markovnikov's addition.